All right, let's get started. Thank you so much for joining. This is Exploratory online seminar number 87. Today, I like to present correlation. Specifically, I'm sure like many of you guys know the correlation or association, if you will, but how to sort of like discover those correlations in the data and how to investigate the relationship effectively with Exploratory. That's the part that like I like to really focus, like how you can actually do it. And there are 4 ways I'd like to introduce today. That's the main topic. Before getting into, let me introduce myself. My name is Kan Nishida, CEO at Exploratory. Exploratory is the company that we started it back in 2016 to democratize data science. Since then, we built and provide the tool called Exploratory that make it easier and then more accessible for various data science methods. And also, we provide this type of seminar and the training through that. Like we try to democratize data science with by sharing our knowledge and skills. Our vision as a company is that like we believe in the data-informed decision is the essential part of for making the world better. So therefore, what we can contribute is to democratize data science so that like more people can understand their data by themselves and in a much deeper way. When we talk about data science, we usually use this framework or the diagram. So usually like you start with the questions you want to answer, then you want to access the data, find the data, and then you prepare or clean up transform that data so that you can visualize or analyze with various methods and chart types and algorithms and so on. When you find it, there's some useful insights, then like you want to share that knowledge or insights with other folks. So the communication is also the important piece of the whole data science workflow. Exploratory provides a modern and simple UI to make these 5 tasks of the data science easier and more effectively. Okay. Enough about myself and Exploratory. Let's get into today's seminar. So online seminar number 87, correlations. Today, I'd like to introduce 4 ways to discover and investigate the correlation effectively with Exploratory. So here's the agenda. I'd like to start with why correlation, or why you care about the correlation and what is the correlation. And then go through those 4 ways to discover and investigate, starting with visualization by using charts. And then the second is a summary, using a summary view in Exploratory to investigate the correlation or relationship among the value in that data. And then like, I'm going to go down to like a correlation analysis and PCA. These 2 you can find under analytics view. So I like to introduce by walk you through. But okay. So why correlation? So there is a great ice hockey player called Wayne Gretzky back in the days, and he made a comment says, I skate to where the puck is going to be, not where it has been. And this is, I think it's a really cool thing. It kind of makes sense and it kind of obvious, but at the same time, you get surprised how many of how many of us cannot do this. But anyway, so the prediction, what that's saying is really trying to do the predict, right? Like where the puck is going to be. So for example, in our business case, let's say to predict how many customers we will have. Then, like we just said, like we will have like 1,000 customers by end of this year or quarter, whatever that could be. Then if you can predict, then you can make decisions on preparing for, let's say, like how many staff and resources you need, or what training you need to provide for your staff, or what type of system you need in place, and so on, right? So the prediction is very important. But then there was another great player called Kan Nishida in ice hockey. I just made it up, but his thing is, I control where the puck is going to be, not the puck controls where I should be. So the control is another element that's important as prediction, because then what can we do to make that happen? It's not like you're just predicting, like you want to actually control where the pack is going to be, or in this customer case, hey, like instead of like just predicting 1,000 customers at the end of this quarter, no, we want to make this happen. Like we want to have 1,000 customers, right? So then what you can do, so the left-hand side the prediction is that if the weather will be warm, then we will have more customers. You just predicted the weather. But the control is like, hey, you know what? Like we want to offer 10% discount so that we can get 1,000 customers or whatever. So that what we are doing here is basically the building hypothesis, right? So like the offering the 10% discount, that's the hype, and then we're gonna get more customers. That's hypothesis. And then if that is right, then we can actually get the outcome. So, but that's just a hypothesis, right? So like you have to test it. And how you test it, well, like you want to collect the data and then see like that is going to really happening or not. And typically you do like A/B tests, right? Like you create two groups and randomly selected, and then like one group like you actually does that action, and then the other one like you don't do it. It's called placebo. Then like you compare between the two. That's basically a kind of nutshell for like trying to find some that causal relationship between the two. But this type of thing is called confirmatory analysis. What it's really doing is that like you have the hypothesis, and then you want to confirm that hypothesis is right or maybe wrong. And by collecting the data, observing the data, and then try to understand between what you thought and then what is really happening. And this hypothesis testing is that I have been doing over the past couple of weeks, going through like a different type of methods. So that's we have done. But here's a question. How can we build the hypothesis? Well, like you have the data, but sometimes, you build the hypothesis from the data, but typically you have your own business, like how you increase the customer, how you get the 100 customers. And maybe, like you kind of know, maybe like some kind of intuitive sense, like, oh, like we do the advertisement. And then if you put the advertisement on Facebook, you usually get like 30% up, or maybe like you provide a discount, right? And the 10%, then we're going to get more customers and so on. But sometimes those are just intuition. And then that doesn't mean that's correct. That's why like you want to do that testing. But what if like you get that hypothesis from the data? Not just intuition. Intuition really the sense that it's when you have the domain knowledge and you have been working on that area for a long time, it's easier for you to build that type of the hypothesis, right? But if you're new to it, then how are you going to come up with the hypothesis? And also you just happen to be like you've been working in that same industry or whatever the work there for a long time, doesn't mean you have various hypothesis, because most of the time like we have the confirmation bias, so like you kind of get stuck with one thing like, instead of like opening your eyes and for various opportunities. But you have the data in this day and age, so why don't we build a hypothesis from the data? So that is the one thing, the kind of thing is actually it's nothing new about that idea. It's been said, and then especially this guy called John Tukey, he published this book called Exploratory Data Analysis. By the way, our company and our tool Exploratory, the name is actually coming from this Exploratory Data Analysis. But having said that, he published this book, and then basically he was proposing like, hey, we are not really exploiting that data, taking advantage of the data we have, and then we are so stuck with that kind of like a pre notion, or like the kind of intuition, or like the pre-built idea. Instead, like, hey, here's the data, we should explore more and then build a lot of hypotheses from the data and investigate. And then maybe like you go through, you go to the next stage as a confirmatory, do the confirmatory analysis and so on. So what the exploratory data analysis really is you start with data, Then you explore the data to build the hypothesis. And then so that like you can actually, go to the next step. So exploratory data analysis is really an exploratory and iterative process of asking many questions and find answers from data in order to build better hypotheses for explanation, what is really happening, why this is happening, and prediction, what is going to happen, and control, how you can make that happen, right? So, but the important piece is asking many questions and finding answers from the data. And also to build the hypothesis. It's not like trying to find answers, just you want to build the better hypothesis. Okay, so then what type of the questions that you want to ask is that, I think it's the most important question in this EDA is that, are there any variables correlated or associated to one another? And if so, how are they correlated? And I think that's really the main part of that data analysis. So not necessarily just for the EDA, but any type of the data analysis. What essentially we are trying to do is find the relationship, particularly the correlation, association, and so on. So I use the correlation association. The reason I use it, I'm going to explain just a little bit later, but it's really a relationship where changes in one variable. In this case, a variable, if you're not familiar with it, it's just a column. When you have the table data, it's just a column. And then changes in one variable happen together with changes in another variable with a certain rule. So you expect those two things that are moving in the, doesn't have to be the same direction, but in the same way, or same pattern at the both variables. Okay, so next is what is correlation? So I start talking about the correlation and association. It's basically the same. I usually just use correlation. I'm not a academic person, so I don't feel like we necessarily need to separate. But the correlation is often used in the sense that more about the two numerical variables relationship. And then more precisely, it's more like kind of a linear type of relationship. But for here, for the sake of simplicity, it's more like numerical variables, the relationship between the numerical variables. Association, it comes in like the categorical variable. It's not just numbers. It can be the groups or character related character-based groups. So for example, like California and Florida, those are like a categorical, like if it's the variable name, the region or state or something like that. And then another one is maybe, can be the GDP, and then what's the relationship? Or maybe like what are the political party association or something like that, that can be the categorical variable. So category and the category, or category and the numerical. So anyway, like when you have the categorical variables, most of the textbook in the statistics world says association. But not bad, actually. So something like this, right? For example, when you have a country and then the other ones can be category or numerical, but in this case, monthly income, then US is higher than UK and higher than Japan. So it looks like there's a relationship based on the country that we can expect different monthly income or something. And then the correlation is a numerical. So like age and monthly income, both of them are numerical or the numbers. And then in this case, for example, like as the older you get, the higher the monthly income you get, type of the relationship. And then we have something called correlation or correlation efficient. So you can express the strengths of the correlation or correlated relationship as a metric or number. And then typically we use this -1 to 1. The most right-hand side is that when you get to 1, that means that the two numerical variables have the strongest you can expect as good as it gets, the strongest positive correlation. So it's almost like you can draw the line, and then all the dots in this 5 or 6 dots can be like an employee, can be the customer, whatever that could be, all lined up on the straight line. That means one variable moves, the value in one variable moves, and the other like a variable in the other variable moves in a precisely expected way. And the most left-hand side, that's the strongest negative correlation, which is -1, is the opposite. So one variable in, the value change in one variable, like if the value goes up, then you can expect the other variable's value goes down. So it kind of moves the opposite way. So that's a negative correlation. And then at the center is 0. When you get the correlation metric says 0, that means there's no correlation. That means you can't expect any way. So like one variable change, and then like you can't expect even like a change or which way it changes. You just like it's very random. So this type of relationship can be called independent. But typically, any type of variables, when you try to investigate the correlation, usually between a 0 and 1 or 0 and -1, somewhere between. And then like when you get some numbers like 0.7, 0.8, then you can sort of like assume that there is a relatively strong relationship. When you get 0.2, then weak relationship. But there is some relationship, but that relationship is not that strong. Okay, so why these association or correlations are important? I think here is the really the point, is that if we can find the correlation between two variables, in this case, let's say monthly income and working years, and then we can predict or expect based on a value in one variable. In this case, working years, if it's 20 years, then we can expect this person's monthly income would be somewhere around $15,000 or something. So what we have just done is that like monthly income has a variance from like, let's say mean value to max value, like $1,000 to $20,000. So the value is very valid. There's a variation, right? And we call it like uncertainty. But what we just happened is that we found that correlation between monthly income and working years. Then because of that, like now like we can reduce the uncertainty, meaning we don't have to say like, oh, maybe the monthly income it would be between 1,000 to 20 and 20,000. Instead, we can actually say 15,000. No, it doesn't have to be exact, but it can be around 15,000. So that's basically is helping us to predict, what the monthly income would be based on the working years. Same thing with the association. So one variable can be category, right? So in this case, the country. But if there is a relationship between a country and a monthly income, if there's no relationship, in any country you go, you'd expect, same around the monthly income, or it doesn't really matter. Then that's useless. But if somehow the monthly income is different among the countries, then once you know which country this person is, then you can expect what monthly income would be. So that, again, we are reducing the uncertainty or reducing the variance. Okay, so if we can find strong correlations, it makes it easier for us to explain how monthly income, in this case, would be, or to changes. So basically, we can explain what's the logic behind it, like what matters in terms of deciding monthly income. But not only explaining, but also we can predict what the monthly income will be. Okay, so we've been talking about correlation, but then like when we talk about correlation, even including myself, it gets kind of like confused with the causation, because it's very similar. And then we tend to talk in the language of causation when we explain the correlation. So like I just wanted to make sure, like, these are two things can be same, but can be different. So if whatever the relationship you find, that can be just correlation, but not the causation. Sometimes that's actually turn out to be the causation too, but most of the time it's actually not that simple. So anyway, so causation is a special type of correlation, but that doesn't mean those are equal. And then But that's why at the very beginning I talked about it's like hypothesis test and A/B test. So like you want to actually deploy the A/B test or randomized control test, whatever that you can do to make sure that relationship is actually causation or causal relationship or not causal relationship. Anyway, if we can confirm that a given correlation is causation, that is the best case, right? Because then we're talking about controlling the outcome the way we want, right? Because as long as we can control that one of the variables. Anyway, so I talked about more detail in the past seminar called correlation and causation about that difference and also how you investigate that stuff. So if you're interested, please find that past seminar. You can actually go there from the online seminar page. Okay, anyway, having said that, put that aside and then how we can discover and investigate correlation. Let's get into that. So there are 4 ways. I'd like to start with the visualizing correlation first. So I'm going to use the employee data. Employee data is like each row is about each employee. And then there are about like 27 attributes like age and income and then what job role and monthly income and so on. Okay. And I like to quote another great quote from John Tukey. Far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. And I love this quote because I make these mistakes all the time. So like it's always I try to remind myself to get back to this comment. So it's always like, what is the question? So in this case, let's say we have the salary information in this data. So like we want to understand how the salary is decided. Because when I use a histogram to try to visualize the distribution of the salary or monthly income in this case, even though the average or mean is $6,503, but there are a lot of variance in data. So the question is, what makes monthly income different? What is this variation is coming from, right? So like what makes that different? So start with visualization, and I'm going to start getting to Exploratory right away. So here is that data, table view, and then summary view. And then like when you look at the monthly income here, this is the one that we are interested in for this particular segment. Okay, so I like to know how, where's the monthly income? Did it disappear? Here, okay. So I like to know like what makes some employee high income and what makes some employee low income. Okay, so we're gonna go to the chart. Typically, this is kind of like one way to do it, right? So like you go, we are talking about monthly income, which is numeric. So I'm gonna start with a scatter, and then typically I think I would recommend you assign that what you are interested in. So in this case, monthly income to the y-axis. Then what x-axis is something that like, you think might be related. For example, the age. Maybe like older folks have tend to have like a higher income, and then younger age tend to have like a lower income or something. So what just happened here with the scatter chart is the x-axis age and the y-axis income. So then like age is older, then I was expecting that sort of like these people, each dot is actually each role or employee in this case. So there are a lot of people right-hand side top corner. However, there are some folks on the right-hand side bottom as well. So these guys are like older age. However, the income are not that high. But here, you expect, for example, the younger age not have like high income, and then that's actually correct. I mean, there are not many people getting high income, almost like none getting high income if you are like less than 30 years old. So there is some kind of relationship. It's sort of like from left-hand side bottom to right-hand side top. And you can actually show what that relationship is by using that something called trend line. So from the y-axis menu, there's a trend line. And then from there, there are various options, but you want to use linear regression to just get that correlation. So for example, here, if I click on apply, and then there's a lines being drawn. So this line is, it says linear regression. What that means is behind the scene, it builds a linear regression model by using monthly income as a target, age as an exploratory variable, or like a prediction variable. But what it's really doing here is that draw the line in the middle of all the data points. Okay, and a more precise way to explain is that like basically the distance between all these dots and the line to be minimum. I think that's how this algorithm works in the behind the scene. But when you try to do it, then basically it's kind of goes through in the middle of that. So that way it gives us the idea of like overall relationship. It's a very high level, very generic, but overall relationship. And when you move the mouse over it, there are some metrics. Here, the most important thing is the first one. It says correlation, 0.497. And then you remember like the correlation, the efficient value is ranging from -1 to 1. 1 is the most strongest positive correlation. So it's not like a closer to the 1, but at the same time, it's not like a closer to the 0. 0 means no relationship, somewhere between. So I would consider this as a relatively strong, not like super strong or a strong relationship, but a somewhat strong relationship between these two. So there is, I mean, you can say like, okay, there is some relationship, but it's not like once you know the age, you can precisely predict the monthly income. It's not, but still there's some sort of relationship. Okay, so how about the other variables? Like, you can kind of start adding, changing around this. For example, maybe education level, or maybe like there's working years, and then maybe there's some other variables that we can use, right? So that you can kind of start looking around that stuff too. But numerical, at the end of the day, the scatter plot really gives you the good idea. Another way to visualize this type of relationship is to use some other charts. So, for example, let's say like a bar chart, and then here, like I'm gonna use, let's say like a job role at the x-axis, and y-axis is like monthly income. But in this case, I'm gonna change to average, and then I'm gonna sort it. So basically what we are looking at is based on the job role, do we expect the different monthly income? And then there is some differences here. But obviously these two have the highest, right? Okay, so, but this one is basically like we're using the mean of each group and then comparing them and see different, there's a difference or not. This is one way to do it. Another way to do it is because there's a variance in the data, right? So you can actually show that variance of the data for each group by using a box plot. So this one is basically like showing from the minimum value to max value, and then like inside the box, and the line at the center, this is like a median or a 50 percentile. And then the lower part of the box is like 25 percentile, and then the upper part of the box is the 75 percentile. So that means from the medium, center at the medium, we have 50% of people in this box basically. And then like all people starting from here to the mean to the max. So this way, like basically we're comparing not just by using the mean, we are using the whole variance, and then we will try to understand if there's difference or not. There's another way is that instead of box plot, if you're familiar with confidence interval, then you can actually use error bar. I think this is a great way to, another great way to visualize. So here, I'm gonna focus on just the confidence interval and the mean as a dot. Then basically what this can help us is that to be able to identify that difference is meaningful or significant. So meaning like if these lines are, overlapping, then even though the mean is different, but we can't say it's significant. This one is like something to do with a significant level thing or the confidence interval thing, like I talked about more in detail in the past seminar. So the key here, I'm not going to go into the detail, but key here is that I'm going to double click to go back. This gives, basically this line is telling me that we don't know the true mean, but 95% chance that like that true mean resides somewhere in this range. Okay, so so that says if the lines are overlapping, it's not significant. If it's not overlapping, then we can say, oh, these are significant difference. So that's sometimes key, very important, because some mean itself is not really reliable, because especially when you happen to have like only 5 people in this like one particular organization, how can you trust that mean, right? Or compared to like when you have 500 people and then you get the mean, that's more reliable in general. So that's the this is what we are doing, is we're comparing, but at the same time we are trying to understand the relationship between one categorical variable, which is job role, and then one numerical variable in the monthly income. Okay, so in order to understand the relationship, it's not just a scatter plot, but also the box plot or error bar chart, or even like a bar chart can be useful. But are we really going to change this like a variable for every single combination? For example, like right now, like we want to know like what makes that difference in the monthly income, but that means we have to switch back and forth in all these variables in the x-axis, right? So that's actually super cumbersome. So for that purpose, you can actually go to the summary view. That's the second way to discover and investigate the correlation in exploratory. So, and then there is literally like the button called correlate. Okay, so when you click on this, then you get this green banner at the top, and this is a correlation mode. And then you want to actually you can set something called target variable or column. And here, like we want to know what the monthly income, what the relationship between the monthly income and all the other variables or columns. So when I select the monthly income, what just happened is every single column now compared against monthly income. So let's start with the age here. So here, x-axis, the values, I think, starts from like somewhere like 18 to 60 years old. And then it divides into 10 groups with equal widths. And in each group, it calculates the average or mean. And then you connect those data points by line. And that's what you're seeing at this line chart here, with the 95% confidence interval as a kind of like the belt or area. Okay, so that's a numeric. For the categorical variables, like a character, and then maybe something like if you have like a logical and a factor, and then like, but those are categorical variable, then you see you have the error bar chart. That's similar to what we have seen under the chart view. So in this case, you have the mean, but also 95% interval as the error bar. And again, like if these are not overlapping, then okay, this attrition, basically the people quit the job or not, actually have the relationship with monthly income. And then that relationship is a significant relationship because 95% interval, confidence intervals are not overlapping. Okay, so now here, going back, age, the correlation is 0.4979. That's the same number that we saw with a trend line in a scatter plot. Okay, so the correlation, so basically we want to know like what are the variables, what are the columns that have the strong correlation with monthly income. So we can actually use a sort to reorder these columns from the highest correlation to lowest correlation. Let's do that here. If I select the correlation here, and then basically the first one is that showing up job level is the highest correlation number, so 0.95. 0.95, you remember the one is the most strongest, my English is kind of messed up. So the strongest correlation and the strongest positive correlation, right? So that means it's like almost like when you know that once you know the job level, you can sort of predict that monthly income is very high accuracy. But then when you think about it, it's kind of like obvious. It's like, yeah, I mean, probably job level and monthly income is related in any company. But besides that, so it looks like these two are very strong relationship, has a strong relationship. Next one, the total working years, 0.77, that's also. And then the next one, the age, right? And then, but the problem here though, is that these categorical variables doesn't have this correlation. It says Pearson. Pearson is one of the algorithms that can calculate the correlation. Turned out we cannot calculate the correlation between the categorical variable and the numerical variable. So that means even though like we sort it by the correlation numbers, that means all the categorical variables are just sort of like pushed to the end. And that doesn't mean that the relationship between attrition and monthly income is weaker than this like a percent salary hike, which has a correlation is minus 0.02. It's like almost like a zero. Right? It's just because the attrition doesn't have a correlation number, that doesn't mean there is no relationship. So what can we do? Well, there's one way to do it is this R square. Okay, so that there's all the variables have this thing called R square. And R square can be calculated. And how you calculate this is that when you have the correlation, by the way, it's R square is just the square of correlation. Correlation sometimes can be called R. So therefore, like this R square is just literally R squared. Okay. But well, we don't have the correlation for the categorical variable. That's the whole problem, the first problem. Well, in that case here is like it says linear. This means a linear regression. So we built a linear regression model behind the scene, having monthly income as a target and attrition as an explainer variable. Okay. And then we compare against something called null model. And the null model means like it's always predict the average or mean. And then like basically they calculate how better this model based on this attrition variable performs compare against the mean model or null model. Okay, and then so that way like you can calculate the R square. Well, it turned out the same way the correlation calculated too, except correlation is actually the root of R square, like opposite of square. So basically, both of them is mathematically doing the same thing. It's just that, attrition case or categorical variable case, it takes one step to create a linear regression model and then to calculate R square. But having said that, all the variables that way, we can calculate this R square value in a consistent way. So that means we can compare among all these variables. Another bonus point of this R square is that when you see here, the correlation value can be minus or negative, that means a negative relationship. There can be like minus 0.9 or something. Minus 0.9, even though it's negative, but that's a pretty strong correlation, right? But if you order by the correlation number, then the bigger minus number going towards the end of this line, right? Because like we literally order them by the number itself. But we don't want that. I mean, sometimes you want that, but if you care about the strength of the relationship, no matter if it's positive or negative, you want to see the strong related variables to show up at the kind of like a top, right? So by squaring the correlation value, then it's always the positive numbers. So the R square numbers is zero, starting from ranging from 0 to 1. And then closer to the 1, meaning the stronger the relationship is. So I'm going to use R square to sort all these columns. And that way, here, the first one is job level, still job level. It says 0.90, which is a square of this 0.9503 something. Okay, so this one is the strongest, and then it's closer to 1, so it's pretty strong. But the next one, the job role, this is a categorical variable. We didn't have that before, but because we have R squared value 0.81, again, it's closer to 1. It's pretty strong relationship. So that means based on job levels, I mean, we can sort of like reduce uncertainty or variance of the monthly income. So a job role is pretty reliable information to know when you want to predict monthly income. And the next one, the total working years and the age and the attrition and so on. Okay, so that's kind of a quick way of like finding the correlation among the variables. In this particular case, though, like we know what variables we are interested in this case, monthly income. Then like we want to investigate, like, I mean, this, whatever the relationship for all the combination against monthly income. Okay, so another thing like also is that here's a p-value. And then this one is, it says KW test. This is a classical Wallis test. And that's exactly the seminar that I did last week. I think I have done the last week here. So you can actually go to our training page or seminar page, and then you can find a past seminar, and then this classical Wallis test is the one like we have done before. And this is used to say, basically, what is the chance that, if you accept a null hypothesis, what is the chance that you get this kind of relationship, whatever the thing that you're seeing in front of your eyes. So when you said this is like a less than 0.0001, that means like it's 0.01, less than 0.01% chance that you're going to get something like this if you accept the null hypothesis, meaning there's no relationship between job level and monthly income. And that's impossible, like it's happening here. So therefore, if you see like the number closer to 0, that means the relationship is significant. So let's say, for example, here, this one, business travel. Depends on business travel, are we going to have the different monthly income? The mean is different, but the confidence interval is overlapping. So that point, we already kind of know like the relationship is not that significant. But by looking at the p-value, 0.53, that means 53%. 53% of the chance you get this kind of difference between here, the mean is different, but this kind of difference you'd expect. So, 1 and 2. So that's kind of like a commonly that could often happen. So therefore, we can't reject the hypothesis. Therefore, it's not significant. So there is that information. This part is actually sometimes important because let's say, something like this, attrition. R squared is 0.02. Isn't that so small? Like, it's close to 0. So does that relationship matter? Well, yeah, it's not that strong relationship, but by looking at the p-value, it says that relationship is significant. So we can say like that there is a relationship between attrition and monthly income. It's just that like seems like the correlated relationship is kind of weak, but there is a relationship. So you can use these types of information to investigate further as well. Okay, so this one, like, so far, we basically look using this correlation mode to find any relationship with one particular variable, in this case, monthly income. But sometimes you don't really have the one particular thing. Even this data, I got this data and I want to just understand overall pictures by finding the relationship among the variables, not with monthly income. I like to see, like, for example, like job level and age are related, attrition and age are related, and so on. So among all those variables, I like to see what the relationship is. But today, this case, like I like to focus on just numerical variables. There are two things you can do. One is going to analytics view, and then something called correlation. So let's try to do it here. I'm going to click on plus button to open the new analytics tab. And then I'm going to select, here's a correlation. So this correlation is basically allows you to discover the correlation efficient, that number, you remember from -1 to 1, for every single combination that you based on the variable you selected. So here under the variables, you want to click, and then from I click the age and all the way down to work-life balance. And notice that like I can select only numerical. If you happen to have like a logical, actually, like if, for example, if I go down here, I'm going to just move this one pin to the third step, because this third step, oh, let me just go back to summary view. Here, this attrition, that attrition column is being created here. And then how it's created? Well, what used to be yes and no. But if it's yes, I wanted to make it as a true and then otherwise false. That's the third step. I created this formula, attrition equal double quote yes, right? So like this one is a logical column now. And then here, if I go to the variable, then I can select the logical as well, because the logical is a true, false. The behind the scenes, actually true is 1, false is 0. So we can treat it as sort of like a numerical value. That's why like we can calculate the correlation efficient numbers. So anyway, so from age to work-life balance, oops, what did I just do? Okay, so from age to work-life balance, by using a shift key, I selected all of them and I click OK, and then click run button. And this way, like I can see all the correlation numbers. I can calculate the correlation numbers for every single combination. The cool thing about this is that, like, okay, here, left-hand side top, these are the variables closer or like have the good, I mean, some sort of like a correlation. And then let's say the job level and the total working years 0.78. That's the same correlation number or efficient numbers. So 0.78, 0.8 almost is a pretty strong relationship. Here, monthly income and job level 0.95. That's the same number that we saw under the summary view correlation mode. Okay, and then another one here is that I can see like performance rating and performance salary hike 0.77. These two variables have the strong relationship. And this is the kind of information that like we couldn't find under the summary view, because that one was like basically like we were trying to understand the relationship with monthly income and all other variables. But this one is randomly like these two variables have a strong relationship. And then this one, basically the scale is -1 to 1. So that's the correlation scale. -1 is, I mean, like closer to -1, the negative relationship becomes blue color. So here, like, when you see like this bluish color, that means all these were negative relationship. For example, attrition and the total working years, it's a small number, but it's like -0.17. It's like a negative relationship. That means, I think, yeah, anyway. So then you can actually click on this button to show all the correlation numbers. Or another thing is that, okay, so this -0.17 or 0.02, these are small numbers. You said that sometimes like there's a significant relationship, but sometimes the marginal difference. So how can we investigate that? So we can actually go to the significance tab, and that answers that question. So here, if you move the mouse over, it shows the p-value, and the p-value is greater than 5% or 0.05, and it becomes gray color. It says not significant. Otherwise, red means positive, blue means negative relationship, or negative correlation value. Okay, so here, obviously, these are like a big, the size of the circle is based on the correlation number. So like that when you see the bigger ones, so that means in this case, for example, job level monthly income 0.95. That's why this circle is the biggest. And then the smaller, the gray one tend to be small. And then not only, but even the small around here is small, but this one, correlation is 0.05. But the p-value is 0.04 or 4%. So therefore, right now, the significant criteria number is like a 5%. So this is less than 5%. So therefore, it's significant. So that's why it's red color, not the gray color. Okay. So this one, like I like it because it gives me better idea of like what are the relationship I should focus by taking into account that if that relationship is significant or not. Okay. I think here is the significance. You can actually set that threshold. Hey, I don't like the 5% thing. Like I like to set like 1% or 0.1%. You can actually change that setting as here as well. Okay. And then, so that's the correlation. And then another thing, and then today's last topic is the PCA. So up to this point, it's pretty kind of intuitive. It's not, I don't think it's that crazy. By the way, I haven't done in this exercise because I don't have much time, but you can actually use a repeat by to create a bunch of this heat map charts or even a significance charts as well. So basically creating for each job role or each, maybe region or something like that as well. But today, I'd like to do one more thing, which is a PCA called Principal Component Analysis. And then this one is actually, I like it because it gives me like an overall picture in a very like a visual, intuitive way once you get used to it. Because first, it's kind of like a weird idea because it generates a new set of artificial dimensions or components that are created in a way that they are not correlated to one another. And that can carry as much information with the original data as possible with fewer dimensions. That's the part that it's kind of like, what are you talking about? Well, so let's see like how the PCA works, right? So how PCA finds a new dimensions. So basically come up with the new dimensions. So right now, like let's say we have like a 15 variables, 15 numerical variables, like job level and monthly income and then age and so on. But we're gonna create completely new set of variables. And then when we create those, we want to create fewer dimensions to express the same amount of information with the original number of the dimensions. So originally, like we had 15 dimensions, but maybe we can just, express that, information with 2 or 3 or 4 newly created, artificially created dimensions or variables. That's what really the PCA is. Okay, so first in the data, the multi-dimensional space is so, more than 3 dimensions, it's almost impossible to even imagine. So let's just imagine like only 3 dimensions. That means 3 variables, age, job level, working years, or something like that. Then find the center point of the whole data. And by the way, here, like when I said like information, is basically what it really means, variance in the data. Okay, variance meaning, for example, income from 2,000 to 20,000 or something like that. Okay, and again, each dot represent each employee, and then the center, the green is the center point. Okay, then the next thing what it does is like, hey, which direction has the highest variance? Okay, and if this is a 3-dimensional space, so like that line can be not like X or Y or Z, it can go to kind of like whatever that direction it goes. But this way, the red line has the highest variance. That's why we draw that line. Okay, so and then this becomes the first component or first newly artificially created dimension. And then next, find the direction. Here's the key that is orthogonal to the first component. Okay, the first component is a red color. Then now that we're drawing the second one with a blue color. But then this one is not gonna go parallel to the first one. It goes orthogonal to the first one, but has to go to the direction of has the highest variance, which becomes the second component or second dimension. So now at this point, we have 2 dimensions. And then maybe, this one, the reason we are doing this is to express as much information as the original data has. And then the next one is like, okay, find the direction that is again orthogonal to the first and the second component, yet has the highest variance. And that becomes the third component, in this case, the green color, green arrow. And then we repeat this process and like again and again until the last nth component. So typically, like when you, let's say like when you have 15 variables, then we end up like having 15 components or dimensions. So you, but as obviously, like you, as you notice though, like the more you have, then it's not many variants will be left. So the first one tend to have like a much variance, and the second one is shorter, and the third one shorter, and so on. So that means the first couple of components have the highest amount of the information that original data with original variables had. Okay, so anyways, let's do this one first, and then that probably will give you a better idea. So I'm gonna click on the plus button, and then here is the principal component analysis PCA, the first one from the top, and then variables. I'm gonna do the same thing from the age to work-life balance, and select all of them. In this PCA case, you can't select the logical. Has to be purely the numerical variables, because the logical is only 1, 0. There's not much variance. So only numerical. And then click OK, and then run. And then what just happened is basically, you remember, like we have to select how many variables we selected. 17 columns, 17 variables. And then this is like a first component is the x-axis, and second component is y-axis. Okay, and with these two, how much of the information we can actually express. And that's something that you can actually go to the variance tab, and then you see like the first one is basically 20% of the original information is being expressed in the first component. The second one is 11, and the first and the second, we have like a 31%, basically these accumulated numbers of the original information or variance can be captured by using these two. And these two are expressed as x-axis and y-axis. And what this means is though, on this two-dimensional space, we somehow managed to express all these 17 variable information on this two-dimensional space. In reality, if we have a 17 dimensional space and we can visualize it somehow, like we managed to do it, then we don't even have to do this. But we have only two-dimensional, x-axis and y-axis. So therefore, we just put them, all those information in there and flatten out on this like a dimensional flat area, then this is what you get. So what this means though is that all these lines, right now they're kind of like super crowded. Here, job level, monthly income, working years, and even the age, these are pointing to the same direction. So that means that this is similar information because they're correlated to one another. And here, like the vertical dimension, PC2, there's these guys are almost like along with the, like a y-axis line. This is a performance and the rating hike. Here, performance rating and then percent salary hike. You remember these two are also correlated by the correlation analysis. So that's why they're pointing the same direction. So having said that, these are related variables. These are related variables. That's why they're pointing the same direction. But at the same time, these are like 90-degree difference. That means they are not related between these two groups. It's just going to a different direction. Okay. Or like orthogonal direction. So having said that though, like in this case, another thing is that these dots are each row or each employee. So that these folks, these employees have the higher scores on these two variables. And for another one, these guys around here have higher values on these variables, like longer working years and older age and a higher salary and a higher job level and so on. Okay, so this one, because if we can kind of like visualize the relationship among the variables, but also variables and employee or like roles in this case. I'm gonna remove this like a performance rate hike, percent salary hike and performance rating, these two variables, and then click OK and then run. So basically, I just remove this one. And then I wanted to see like what are the relationship among the rest of the variables here. So then like this gives us like a slightly different view. Now here again, like monthly income and then job level, these two, it's super crowded here, but it's almost like going to the same direction. That, we already know by the correlation analysis and the summary view, these are highly correlated. You remember like 0.95 or something like that as a correlation number. So that's why it's pointing the same way. But total working years is kind of same way, but it's not precise, and age as well. So just looking at here, these are correlated. These are the kind of similar information, sort of like an x-axis way, right? Like, but not exact, like monthly between the monthly income and the job level. I like to just use that slide to explain a little bit more because this chart is called biplot. If you're not familiar with it, you get confused. What the hell is this? But once you get familiar with it, it's so convenient, useful chart. So that I want to, even though like it's a time already 1 hour, 1 o'clock, but I like to spend a little bit more minutes to explain this. So by using two artificial created variables, in this case, PC1 and PC2, right? It try to express the relationship in the data as much as possible with the two-dimensional space. So all these gray lines represent the original variables, let's say like age and working years and so on. Always start from 0 and 0, x, y is 0 and 0, and it shoots out to outside or extend out, okay? And then the variables so have the longer lines. That means these are the ones that can be explained, can be expressed by this PC1, PC2, or x-axis, x, this two-dimensional space. On the other hand, that when you see the variable lines are shorter, that means those are not fully expressed in this two-dimensional space, like as much as the longer ones. Okay, so in this case, like we can see like number of companies, the education at the top, or like a total working years and age and monthly income and so on. These are well expressed in this two-dimensional space. So we can see that relationship very clearly. So what that relationship is, the closer the variables lines means that they are highly correlated to one another. And then these dots, or each employee in this particular case, or each row in general, like then you can see, oh, okay, these guys have the higher numbers on the total working and monthly income. Not a lot of people, right? The majority of people are the kind of like a right-hand side, but some people on left-hand side closer to like edge of these variables. That means they have the higher values on these variables. And then, for example, I pick the total working years. So always start from 0, right? So the 0 going outside on these gray numbers, like outside is like a long working years. Okay, so I'm going to use the mouse, the pointer here. So these area, so like any employee around here have the higher values. And as opposed to that, the opposite side, okay, the way opposite side cross 0. That means these people have the smaller numbers, in this particular case, short working years. The other variable is the same too. Like this is like monthly income and job level. So like people here have the higher numbers on the job level and the monthly income. But when you go to the other side, the lower numbers. So that's just a direction. So it doesn't have to be. So for example, here, okay, how about a between? So that means these people have the smaller number of the working years and smaller numbers of the monthly income. And so it's all relative relationship between the employees in this particular case and the variables. So that's why this one is so useful, because you can see the relationship among the variables, but also second, you can see the relationship among the variables and also the data itself. Okay. And another thing you can do is here, you can use this color and you can assign, for example, what type of people are these here? Like why these people are like a higher age and higher total working years and monthly income. Then you can actually assign, for example, maybe the gender makes a difference or job role makes a difference. I'm going to assign a job role and then click run button. And then here, clearly, like I see a lot of red color here. And also when you look closer, there's also this brown. So red is a manager type of people, job role. Brown is a research director. Okay. So these are the people that have the higher income and longer total working years and a higher job level. As opposed to that, the other side, those are numbers are lower. And what type of the people are lower? So these are laboratory technicians, these are research scientists, and the sales representative. So these folks are, have the lower numbers on these variables. Okay, so it looks like, because we already know by this time, by summary view or correlation analysis, that a job level and monthly income has a high correlation relationship or associated relationship, right? So that's kind of makes sense because based on job level, we have different monthly income, but not just monthly income. Like we are looking at using the total working years, even the age, where these people are kind of located. Isn't this amazing? Because we are talking about like 17 variables and then like 1,470 people. And then that relationship, we just put that thing in this two-dimensional X and Y space. And then this is what we are looking at. So this is very like overall picture. It's like, 3,000 feet picture of that data. So this can be sort of like a starting point. Okay, maybe these are the relationship variables closer to each other or coordinated each other. And then like, there are some people, that higher values or lower values, and then based on which variables and the people here and there, a lot of information can be obtained from this chart. Okay, so that's the PCA, and typically, like once you get the overall pictures, and then like you might want to go to each combination of information, if it's a significant relationship or not, how high that correlation number is, and if you know what particular variable you're interested in, and you want to find the relationship between that particular variable and all other variable, then you want to go to the correlation. And then instead of going to, today I started with the chart, but you want to start from like this, summary view. Then like you can, let's say like, hey, you know what, like, I want to visualize this total working as well. It's already visualized, but also the other option is not just this line chart. You can actually use a scatter chart. So for example, if I select create scatter chart, then you get the scatter chart. So instead of going to the chart view and assigning X and Y and doing the trend line, you can automatically, instantly create the chart as well. Okay, so that's pretty much it for today. So basically today, like I covered number one, how you can visualize the correlated relationship or associated relationship. Second, use a summary view to find or discover and investigate the correlated and associated relationship instantly. And then third is going to the analytics view and use the correlation analysis to find the correlation values for all the combinations, and also test the relationship, the strength of the relation, and significance of the relationship. The fourth is using the PCA to understand the overall pictures among the variables and and all the roles or the employee in this case. Okay, so therefore, and then at the beginning, I was talking about like why correlation is actually the most powerful and the most useful tool any data analysis you do. Okay, so that's it for today. So having said that, please check out our training and seminar page. You can go to our website, exploratory.io. Under the Learn, you go to training seminar. You can access all the past recordings, seminar recordings. And also, if you are Exploratory users, then make sure to check out this how-to tutorials or the video page. We keep publishing tons of contents there. So hope those are helpful. And also, don't forget, we have the Twitter account, Exploratory Data, and that's where like we not only announcing the seminar information, the product release information, but also sometimes tool tips or like what the how to do also like some particular subject, we do the thread to explain some of the techniques and so on. So it's pretty useful, I think. So please follow the exploratory data. Or if you have any questions, please feel free to reach out to me at kan@exploratory.io. Okay, so that's it for today. Thank you so much for joining.